Okay, so now I'm really going to start. So for those who are listening online, the plan today, and for you guys too, the plan today is to talk about differential equations because that's what I was asked to do. And then after I finish that, to just take requests. That's the plan. And normally the whole request thing would happen in the Maths Learning Centre, but it's nice for you all to be together, those of you who are here, so that you can all hear it at once. And if you still have questions, there's always the Maths Learning Centre. And I presume your lecturers have consulting hours at some point between now and the exam, but maybe we've already missed that. Okay, so, all right. La-di-da. Now, I'm going to apologise now that sometimes I forget what's in Maths 1M and what's in Maths 1B, because you do differential equations in Maths 1B as well. So if I say something that it really is not in your course, if you happen to know that it's not in your course, just let me know, because sometimes I forget. Okay, so the general idea of a differential equation is it's an equation that involves a derivative. And the aim of it is not to find an answer for x, which is what an ordinary equation would be, but to find a function. Okay, so we have an equation that involves a derivative, and the point is it's a derivative of an unknown function. And the aim is to find the formula for the function. So you might be told that the derivative of a function is x, and you need to find what the function was that differentiates to give x. Or you might be told that the derivative of a function is the same as the original function, and you need to figure out what function that is. Okay, so the point is to find a formula for the function, not to find the answer for it. The answer is not a number, it's a formula. Okay, that's really important, and that's the easiest thing to keep yourself on track when you're solving differential equations. Okay, and usually what you have is the differential equation itself and also a couple of conditions of some sort. So you may... You may also have like conditions of some sort, and so I'll try and do an example in a second. And they're supposed to narrow down what the function is, because an ordinary differential equation usually has multiple solutions, and you want to narrow it down to one particular solution under the conditions that you've been given. Okay, so as an example, we might have dy on dx is x. Okay, that's the differential equation. It has a derivative in it. And you might have the conditions that, you know, y of 0 is 1, for example. All right, so this here is the equation. And this here is the condition. Okay. Usually you'll need more than one condition if you've got more than one level of derivative here. So this is called a first order because it's got a first derivative, but if your equation involved a second derivative, it would be second order, and it would need two conditions to figure out the exact function that goes with it. And I don't think you do second order derivatives in differential equations in Maths 1M, but you do them in Maths 1B. You make a start anyway. It's quite difficult, so you begin looking at Maths 1B, and if you're an engineer, you'll continue doing it in Engineering Maths 1 and 2 in second year, and if you're not, but you still have to do it, you'll have a whole course called Differential Equations 2, in which case you will learn more about that there. So differential equations are really hard, okay? Mainly because integration is hard. The differentiation is easy relative to most other things. There are about 6 rules and they always work. Integration is really difficult, which is what makes differential equations difficult. So just as an example of how I would go about solving this problem, well, it says that the derivative of y is x. So whatever y is, it differentiates to give x. So I need to integrate to figure out what it is. And that's what integration is for. It's the opposite of differentiation. though originally integration was not defined as the opposite of differentiation, it was defined as areas under curves. But it just so happens that because of the fundamental theorem of calculus, they're actually the same. Okay? So when they were first invented, no one thought that they were related. Okay? That areas under curves and slopes, no one thought they were related, and then it became clear that they actually were, and that differentiating, which is what you do to find slopes, and integrating, which is what you do to find areas, are actually the opposites of each other. Okay, so to solve this equation, I would go, well, I need to integrate, so y would be whatever the integral of x is, which would be a half of x squared plus c. And I did that because that x is x to the power of 1, and there's this rule for integration that says that you put the power up by 1 and you divide by the new power. Okay, which is the opposite of the one for differentiation, which says that you multiply by the current power and then you put the power down by 1. And I need to put a plus c because no matter what number is there, if I differentiate this, it will give the answer x. So what I have here is infinitely many possible solutions for what the answer could be. And it's written as a function. And then what I now do is I use this condition which says that I sub in the 0 into here, and it will tell me what c is. So y of 0 is a half times 0 squared plus c. But y of 0 is also equal to 1, as it says up here. So that means that when x is 0, y is 1. And so that's telling me that in fact c is 1. So y is in fact a half of x squared plus 1. Okay, that's the simplest form of a differential equation. The type where you've got derivative equals and that function only involves x's. Okay? Cool. So just for ourselves, when you're learning something new, especially something that involves trying to learn some sort of process, you should write down the process for yourself so that you've got something clear in your head. So far we've got if the equation is something like dy on dx equals a formula of just x's, then what we do is we integrate like our right hand side, and then we have to use sub in the conditions to figure out c. And technically we should write down the final answer. Now, it's actually technically, your lecturers don't really need to tell you this sort of information. It's the sort of thing that you can figure out for yourself. As they show you examples, you can say, yes, this is the list of things that I ought to do. And most of these very simple things, they won't bother because they're hoping you can figure it out for yourself. And once you're used to it, you just do it without even thinking. So my advice for Maths 1A in particular later on is to do the same thing for yourself. Try and make yourself lists of things to do. So that's our basic one. And I'm sure those types of ones have a name, but we'll just leave it as it is. They're just plain, ordinary differential equations. Okay, now you may not have conditions, in which case you will just stop there. Okay, because you'll just leave a plus c in it, and that's called the general solution. Okay, so back here.
Question.
Yep.
Is that also called an antiderivative?
Yes. Technically it is an antiderivative. So you know how I said they didn't know that integration and differentiation were the same? Well, we're opposites. So before they discovered that, they had differentiation and anti-differentiation, and they had integration over here, and it just turned out that anti-differentiation and integration turned out to be the same thing. So finding an antiderivative is the same as integrating. Okay, but that's called an indefinite integral, right? Indefinite integral, which is the same as you just said as antiderivative. Okay, either way. Yep?
Will they use those terms interchangeably during the exam?
Probably. Your lecturers are probably going to be careful, and they'll be more likely to use antiderivative if that's what they mean, because that's how they've taught it to you. but sometimes they'll forget, so they'll just use whichever one. And they'll tell you to integrate, and they won't tell you whether it's an indefinite or a definite every time, because the definite will be obvious because it'll be from x, from like it'll have little numbers on it, like from x equals something to x equals something else. So if they don't tell you that, it'll be definite.
We haven't done any definite stuff.
Yeah.
1M anyways.
Haven't you?
No.
Oh, how distressing. There's heaps of it in Maths 1A, maybe that's why.
Right.
Maths 1A calculus is pretty much in...
Yes.
Maths 1A calculus is pretty much differentiation. No, integration. Maths 1B, you come back and you do differentiation again. More so. Okay, yeah, so it sounds odd that if you were coming straight to uni without doing 1M that you would do integration first. That sounds strange, but that's the way they do it. Because they assume that people have done differentiation before and they want to start integration from scratch with the whole, from first principles, like you've done differentiation from first principles, you do that with integration. And integrating is a much harder skill to learn, so they try and get it out of the way first. Okay, so, right, so here you have your ordinary type, and this integration here might have to happen in any of the methods you've learned for integrating. So, what methods of integration have you learned? Just guessing the antiderivative, is that all you've learned?
Integration.
Yeah. Have you given any named methods for integrating? Have you done substitution in Maths 1M? Okay, all right. So, in general, it will be happening to know what the integral is. Okay, so, which is technique 0.
Other than
Right.
just like splitting it up, like
Yeah, other than just doing the integrals separately if there's pluses between them. Yeah, that's right. That's up to you to check that. So good to go and have a look at the ways you know how to integrate. And if you have any questions about that, we can do that later. The next type of differential equation that you know how to solve, and I think is the only other type that you know how to solve, is the separable kind. Well, the next type you've been told about, right? Not necessarily know how, that's up to you. So the separable does not look like the one you've got there. Okay, what happens is that you've got the dy on dx and the formula on the other side is a mixture of both y's and x's. And so it's something like this. And you get something involving x here and something involving y. Okay, your lecturer would call it like fx, gy or something like that. But your separable equation can be rewritten to have something involving x and times something involving y. It may not look like that to begin with, but that's what a separable equation, a differential equation is. So what that means is it's saying, look, there's some formula. If you knew what y was, you could sub it into that formula on this side here, and you would get a formula involving x if you knew what the formula for y was. But you could also differentiate it separately, and you'll get the same answer either way. So let's see if I can have an example there. So this is an example here of something where you do not have to do any methods, right? So let's see, we have la-di-da. Verify that y equals e to the x is a solution of the separable equation dy on dx is y. Right, now you do not have to solve this equation in order to answer this question. The word verify means check. Okay, literally, I don't know if you've ever known someone called Verity, but that name means truth. Okay, verify means establish the truth of. Okay, so truthify this statement by telling me that it is true. So all you have to do is you say, well, y is e to the x, and dy on dx is also e to the x, and so therefore dy on dx is equal to y. because they're both equal to e to the x. That's it. That's verify. It may take longer to do it for some things. So there was one in the assignment most notably recently where you had to verify that, show that something was a solution to the logistic equation, and that took quite some time. But in the end, you were just differentiating it on one side and subbing it in on the other and making sure they come to the same answer. Okay, so the idea is to find the derivative and sub it in here, keep y and sub it in here, and then just figure out if it works. Okay? Yep.
Can you actually solve that?
Sorry?
Show us how to solve
I am going to, thank you. So, you can, however, solve it, okay, because it has more solutions than just e to the x. All right? And I'm going to do a couple of examples because this is the sort of thing that only makes sense after doing several examples. So, solve dy on dx equals y. Okay. So, this is where you actually have to show working and get all the solutions as opposed to just showing that the one you have is a solution. So we do know that e to the x is one of the possibilities because when you differentiate it, nothing happens. So the idea behind separable equations, and I'm going to describe it properly with a better example in a second, is that this bit over here has to be written as something that's in terms of y times something that's in terms of x. So currently there is nothing there for x, so I'm going to do this. It's y times 1. Okay, 1 is a perfectly good formula that technically doesn't involve x, but you can write it as, y equals 1. It's a perfectly good formula. And then what we do is we separate this derivative. Now, most high school teachers would have blasted you with their x-ray eyes for doing that, but we're allowed to do it because we are. We're going to put all the y's and dy's on one side and all the x's and dx's on the other. And because this is written as a division, we're going to treat it as if it is. So we're going to divide both sides by this. Right? And then we're going to multiply both sides by dx. So that's technically 1 dx, right? And then we're just going to put the integral signs in. Technically, I think you're not allowed to write this statement, but it'll do. And that is how to solve separable differential equations. It is magic, I know, but that is how it is. Because you see, this dy on dx is describing what very small changes in y and x look like. So dy on dx says how much y changes when x changes by a very tiny amount. And that says that the amount that y changes by when x changes by a very tiny amount happens to be equal to y at the moment. So we can pretend that this is change in like delta y on delta x. We can pretend that it's change in y on change in x, in which case it is a fraction, and we multiply it all out. And then this is sort of like the area under the line y equals 1, and this is the area under 1 over y. And so those two areas are equal to each other. That's what it's doing. But in the end, you just get used to the whole flipping and changing derivatives, okay? So then we integrate both of these. So the integral of 1 over y is ln y, technically with an absolute value sign. And the integral of 1 is x. And somewhere there has to be a plus c, and we tend to put it over here on the right-hand side. And then our aim, remember the aim is to get to y equals. The aim is to get a formula for y in terms of x. So we need to keep going until we get to y equals. So first we're going to get rid of the ln by doing e to the power of both sides. And notice that what I've done is I've done e to the power of all of this, and that's cancelled out the ln, and e to the power of all of this, and that plus c is trapped inside the e. Okay, it's really important not to just do e to the power of x plus c afterwards, because that's just wrong. Okay, that's why it's so important. It's just wrong. Okay, because whenever you do stuff to both sides of the equation, technically you're doing to the whole expression at once. Okay, and e does not expand out over plus. So we just have to leave it like that. All right. Traditionally, at this point, we would actually split this up like this. Because plus up in the power is times down below. And then we would rename e to the power of c as a number of its own. But I'm going to do that in just a second. So to get rid of the absolute value, we can do plus or minus. Like that. And then finally, all of this, well, e to the power of c is able to produce any number at all as long as it's positive. And then the minus there will produce all the negative numbers too. And technically you can't make 0 there, but it's a perfectly good solution because the derivative of 0 is also 0. And so we say that y is equal to something like that for some a. Probably don't need to write this bit, but as a mathematician, I can't help it. So all of that plus or minus e to the c, that's a. And I don't actually care what c is, because I can figure out what a is from the initial conditions. That's the solution to that. Now it has several pieces, right? We had the piece where we split up the derivative, which is here. That's what the separable refers to. The derivative can be separated. And then we had the bit where we did the integral, which is here. And then we had the bit where we figured out what y was in terms of x. And then we had this final stage where we lumped all of the stuff that was just a constant together into one new constant, which is here. Okay? Right, and if I had conditions at this point, then I would start subbing in here. And I would actually figure out what a was rather than figuring out what e to the c was. Okay. Let me do another example that has y's and x's mixed together. Hopefully this one is not too hard. Coming up with examples off the top of your head is often dangerous. Okay, so I've got dy and dx is y cos x plus cos x. Now currently it does not look like a separable differential equation because a separable equation has this written as a multiplication. And so we have to rewrite it as something involving x times something involving y. So there's a cos x in both of these, so I can actually rewrite that as that. Bring the cos x out of both of these. I've factorized. I've brought the cos x out. And I've left behind a y here and a 1 here. Okay, let's just check if we got that right. If we expand this out, we'll get y cos x plus cos x, so that works. Okay, so I had to do that because separable equations can only be shown to be separable by rewriting them as something in terms of y plus times something in terms of x. So now I can start about solving it. I need all the y's to be over here and all the x's to be over here, and I have to do it by multiplication and division. Okay, so I have to divide by this. And times by the dx. Okay, so the dx has gone up there and that has gone down there. And now I integrate. So you are allowed to put the integral signs in at this point. But if you see it on paper, it's harder to tell what's happened. So I actually did that bit first and then added the integral signs afterwards. So I've done 2 steps in one go there. But you don't have much space on your exam to write, so I would recommend doing that yourself. Okay, as long as you know that you did one bit and then put the integral signs in, it'll be okay. So now we integrate both sides. So let's see, the integral of 1 over y plus 1. Well, if it was just 1 over y, that would be ln of y. And there's this rule that if this thing under here, when you differentiate it, comes out to be a constant, you can just pretend that that's a y and then divide by the derivative. And the derivative of that is 1, so technically it's this. If it had been 2y plus 1, I would have gone half here. All right? Just let me illustrate that on another piece of paper while we're at it. You've been shown this rule, I'm so certain of it, but you need to know it now anyway. So just some examples. If you integrate this, you're going to get this. Okay? And that's because you know that when you differentiate this, it'll work out fine. Because if you differentiate e to the 2x, you'll get e to the 2x times 2 because of the chain rule. And you need that half to cancel out the 2. And if I had right? Oh, crap. Sorry about that. Let's do cos. What's the integral of cos? Plus sign.
Oh, crap.
So the derivative of cos is minus sign. The integral of cos is plus sign.
I did it too fast.
But I'm going to have to divide by that 3. Okay? So that when this differentiates and the 3 comes out because of the chain rule, the third will cancel it out. Okay? And finally, one more. Like that. If it was just a y, it would integrate to give ln, right? But it's not y, it's 1 minus y, and I have to divide by the derivative here, and the derivative of this is minus 1. Technically this, like that. So please be aware that if it's 1 minus something, that there is a derivative there. There is a number, it's minus 1. Okay, so that rule works for all functions of any kind. If I happen to tell you that some function integrated to give some answer, then you would know what to do if I put 3x into it instead of x. I just put 3x instead of x into the integral and then divide by 3. Okay, that's a really important rule. Technically, it's substitution, if you've ever seen substitution before, but it's so common that we just ignore it and do this instead. Okay, I call it divide by the constant derivative as you integrate. Okay, it's the opposite of the chain rule. Okay, with the chain rule, normally you'd multiply by the derivative, but for the integration, you're doing the opposite. You say you're going to divide by the derivative, but that rule will only work if the derivative is a constant. Okay, if the derivative is not a constant, you cannot do this, and they won't ask you to do that in 1m anyway. But the derivative, if the derivative is not a constant, if it involves any x's at all, you cannot do this trick. It will not work. So that's why integration is so hard. Okay, so back to here. That's why it came out as this. It's y plus 1, but I had to divide by the 1 that was next to the y. And then the cos x integrates to give sine x plus c. And this is going to be worlds of pain. So I've got y, the absolute value of y plus 1 is e to the sine x plus c. So what's that? E to the c, e to the sine x. And then y plus 1 is plus or minus e to the c, e to the sine x. So y plus 1 is a e to the sine x for some a. So all of this is a. So y is a e to the sine x minus 1. So I'm doing what you normally do to solve equations, right? I work from the outside inwards. So first I got rid of the ln, and then I got rid of the absolute value, and then I got rid of the 1 that was here until I had y all on its own. The issues that's going on is I'm doing some other things that will make my differential equation work properly. So in between here, I'm dealing with the e to the c to turn it into something prettier. Right, that's pretty much it, except that there are 2 situations where you use them that you don't know how to solve it from scratch. Okay, so you've only been shown how to solve differential equations like this from scratch, and sometimes it's not nearly that obvious. So, where's the top? So there's some specific examples, and I will take your yellow book. There's some specific examples of differential equations you've been shown, and you've just been told what the answer is, but not technically how to find it. Because, for example, the logistic equation, the solution to that is done with a process called partial fractions, which you learn in about week 11 of Maths 1B. Okay? But the solution to it is known. So there are some few cases where you are allowed to just write down the answer because you don't know how to do it by hand. Okay, so let's see. You've been told Newton's law of cooling. So these are what they call applications, right? But I'm going to call them specific uses. Spec. Gosh, specific looks weird in capital letters. Anyway, so you've been told Newton's law of cooling. Which so does not look like I think it ought to. That's not. This is less helpful than you would like this book. I need someone's notes so that I can get the specific version of this, unless someone remembers it off the top of their head, what the differential equation...
T equals T0 plus C e to the minus kt.
Yep.
That's the solution. What was that?
Yep.
Like that?
Yeah.
What's the differential equation look like?
I don't think it did that, did we?
Well, the reason it's in this part of the course is because it's a differential equation. So it's probably worth to know that know what it is.
dt on dt on dt equals negative k t take t naught.
Awesome. Okay.
Yeah, I remember.
So this here is the differential equation, and this here is the solution. Okay, so you notice that C probably came about because of an e to the power of something as you went along. It is actually possible for you to solve this differential equation because it's separable. Okay, it doesn't involve a little t on this side, so it will be like the minus k is probably the thing that you'll leave over here. It's possible to solve this on your own as using the method of separable differential equations. But you've been told what the answer is, and you're allowed to, unless they specifically say, solve it using separable differential equations, you're allowed to just go straight here. Okay? Yep?
In the exam, would they give us the equation?
I have no clue. So I was just asked, in the exam, would they give us this equation? I don't know.
I think he said they pretty much would, same as the logistic.
Okay, so apparently the lecturer said at some point that they would. But this is something that you could maybe email the lecturer or something and ask them because I don't know that, because never having done 1M myself, I don't know, and that was some time ago, so they might have changed the rules since then. When I did first year, you weren't allowed to have calculators, so things have changed. So that's Newton's law of cooling, and often in the situations they give it to you, you have to figure out the K as well. So normally a differential equation only doesn't have any unknowns here, but they're going to tell you what the K is too. And so knowing what this answer is, see, you don't even need to know this, because you can just say that, well, I've got a T0, which is presuming the beginning temperature, the surrounding temperature. So what's this, surrounding temperature? And you've got two unknowns, so if you know what the temperature is at 2 times, you should be able to figure out what the C and the K are. Cool. That's really distressing because T0 would say to me that it's the temperature at time 0. Yep?
I think it's probably meant
TO.
Sometimes you see both TO and T of 0 in the same.
Yeah. And then you can put the 0 in brackets. So you,
How annoying.
yeah.
Yes.
I would say TE. T environment. That,
But then you have TE and then you have E.
no, capital E.
Oh, okay.
Because then it would look different, right, to the little e that's already there. Though I have seen formulas in science that use both a small e as an unknown and the letter E as the number E, which is just annoying. Okay. Yay. And in some courses they use pi as a probability, as opposed to the number pi. Really freaks me out. So all of the examples that work with this will tell you something along the lines of, there's some sort of pot that's come out of a kiln, or there's the beer has been taken out of the fridge, or there's some object that, and it says Newton's law of cooling, but it's also Newton's law of heating as well. So if you put an object that's cold into a warm environment, it will warm according to this formula as well. So it's Newton's law of cooling / warming as well. All right. But it was first applied to things cooling down, but they warm up in the same way. If you put a pot into a kiln, it will work the same way. Okay, and there's the logistic equation as well. So there's the logistic equation, which you definitely do not need to know how to solve on your own. It is separable, but in order to do the integral involved, there's a very clever trick called partial fractions. So the original equation, so the answer is what? It's usually about populations, isn't it? So does someone remember it or can read it out for me?
Capital K.
Yeah, there's an L on P on
There's an L on P somewhere.
Oh, wait, the actual equation is like L on 1 plus A e to the negative.
That's it, L over A. 1 plus A.
Yeah. Yeah.
Yeah.
And then
Differential
in the
one.
brackets above, I know there's a 1
KP
minus.
bracket 1 minus
Yeah.
L on P.
Yeah.
Something like that.
Yeah. P.
Yay. So you do this again in Maths 1B, but the notation's different, just to freak you out. So does anyone know what any of these numbers actually refer to? Any of these letters? Limiting population? In Maths 1B, they call it the carrying capacity and call it C. Do they call it that in Maths 1M? Yeah, possibly in Year 12. So if you know what the limit is, you can put that in straight away, because sometimes they'll tell you that. So if it's like the spread of a rumour in a town, that would be the population of the town. Or the spread of zombieism in a city, that would be the population of the city, okay? Well, it works just as well. Zombieism is just a virus. I read this awesome book that based it all on global warming. Zombieism is a virus, but it only activates a body if the ground temperature is above a certain level, and so global warming made the base ground temperature above a certain level, and all these zombies started reanimating because of global warming. Dear me. I know more about zombies than you would expect for someone who's never seen a zombie movie. So, anyway.
Would you follow Call of Duty zombie storyline?
No. Okay, so it's the same as the other one. There are several unknowns involved, and you just figure it out. But are there any particular facts that you're supposed to know about the logistic equation?
There's a point in the middle.
There's a point in the middle somewhere.
Can't see it.
Yeah.
There's an inflection point, which is this point at which the population is growing the most rapidly. So the point of most rapid growth happens when P is L on 2. Note that it doesn't tell you what time that happens at. It only tells you the population that happens at. Okay, so once you've popped half the population, then that's when it's growing the most rapidly, and it will level off after that. Okay, so do we want to try an example of one of those with actual numbers?
I did continuous compounding interest.
Oh, did you?
Uh-huh.
So that was back when you did technically logs, right, and exponentials. It wasn't part of differential equations, but you did do that.
It was, wasn't it? It was part of another expansion.
But we can do that. We can do that under requests in a minute if you'd like to. So cool. Has someone got an exam or something?
Yes, I do.
Or a particular example they've been struggling with that I can actually go through?
Are we doing logistics?
Logistic.
Which exam?
I wouldn't expect them to have both logistic and Newton's law of cooling in the same exam because you haven't got enough time. But I would expect them to have at least one.
Yeah, I've done no, that one hasn't got one in it.
I don't even know if they put either of them in there, but you can't just hope that it won't.
Yeah, it's not in that one either.
Okay.
Hang on, I think there's one in this one.
So one of the problems at the Maths Learning Centre is I'm not actually involved in your course, so I can't just come up with examples off the top of my head for things that I never studied myself. See, for separable differential equations, I can come up with them off the top of my head. But and the things with logistic, it's supposed to be like a real life in inverted commas example.
None of these exams
Have logistic?
have the logistic equation or the Newton's law of cooling.
Yay! Nice to give you some practice, hey? We'd have to get it from an assignment. So look, there ought to be examples of it in the worked examples in my uni. Okay? Of both of them.
Yeah.
Okay, so if you...
12 had a lot of them in it.
Yeah, there. I remember doing them. So there ought to be examples of both the logistic equation and Newton's law of cooling in the worked examples in my uni. And in assignment 12, I would actually like to get to the answering questions bit rather than wasting time while people are looking for stuff. So I won't do an example of that right now. But the most important thing is to remember that formula is just subbing in the end. You've got to know what the population is at various different times, and you can sub it in. It's the solving of that equation that's the hard bit, and that's what you wanted to see, was it? No? It's the solving of this equation to figure out what k is? No, we're all good? Okay. All right, unless someone asks.
They've got a question in here, like dy 2 over dx squared plus y equals 0, and then you have to verify that.
Can't do maths from across the room.
2010. You just haven't done anything like that yet.
Y dashed is equal to 2y.
The next one down.
Well, I had to start. Read the beginning.
Oh, sorry.
Right, so this was from 2010, was it?
Yeah. I think that's a different question, isn't it?
This is not logistic at all, but you're just asking?
Sure.
Oh crap, that is different.
Yeah.
So this is question 8b. Verify that y equals a cos x plus b sin x is a solution to d squared y over dx squared plus y equals 0. Okay. Right, so I haven't done anything like that because that's a second order differential equation. It has a second derivative in it. But that's okay, because even though you have not been taught how to solve second order differential equations, though technically you should be able to do it with the separable thing, but you've got to think really outside the box. You can figure out if this is a solution to that. Because what we need to do is we need to figure out what d squared y on dx squared is for this. So y is a cos x plus b sine x. And dy on dx, so the derivative of cos would be minus sine, and the derivative of sine would be plus cos. And the second derivative, so the derivative of sine would be plus cos, and the derivative of cos would be minus sine. Okay, so I've found the derivative of y, the second derivative of y, so that's this part of the formula. So now if I add them together, let's see, d squared y on dx squared plus y would be minus a cos x, minus b sine x, that's here, plus y is that, plus a cos x plus b sine x, which is 0. And that's the original equation. So it works. Yeah.
Yeah.
So it is a solution after all, because it satisfies the equation. Because the original equation was supposed to come out to 0, and it did. Cool. So in Maths 1B, you're actually taught a method for actually finding that solution, which involves complex numbers along the way. So that is one of the very few times you have to use complex numbers again in 1A and 1B. There's about once in 1A and once in 1B, and this is the one in 1B. But you don't have to do that, you just have to sub it in. But subbing in involves finding derivatives first. Cool.
Can you do that other one that you scribbled out?
The first one?
Yeah. Y
Sure.
dash equals 2y.
Let's go for it. So I've just been asked to do a different example. So this is actually 8a. And it was just solve this, was it?
Yeah.
And it had some initial conditions.
Y of 0 equals 10.
Okay, so this is separable, but in order to be able to do it by any of the methods that we know, we have to rewrite this as dy on dx probably. But you see how this is involving a y? So if this was involving just an x, we could just integrate it, which we can't because it doesn't involve just an x, which means the only way we have to do it at the moment is by separable equation. So first I'm going to write dy on dx is 2y. And you'll see that this is already two things multiplied together. It's a bit involving y and another bit. And that's our bit that involves x in inverted commas. Okay, it doesn't have any x's, but we're going to treat it as a function of x. So we'll divide both sides by y and multiply both sides by the dx. And then we'll integrate. Sorry? And then the integral of that is ln mod y, and the integral of 2 is 2x. And then we'll have our mod y is e to the 2x plus c, which is e to the c, e to the 2x. And then our y is plus or minus e to the c, e to the 2x, which we shall call a. And then we know that y of 0 is 10. So it means that when x is 0, y is 10. So we've got y is 10 and x is 0. But e to the 0 is 1. Whoop. So a is 10. And therefore, y is 10 e to the 2x. Cool. Is that not what you did?
No, it's not what I did, but thanks.
Now, it would have been possible to actually do move the whole 2y down and do 2y times 1, but it would have made your working less easy. So at this stage here, I could have had 2y here and 1 there, and that would have been fine, but things would have been less happy as you've gone along. Yep?
I feel like after Euler's
Thank you for reminding me. Someone just said, what about Euler's method? Okay, so Euler's method is give up. Euler's method, if you like, if you want to pronounce it properly. Well, he was German, right? So it's, well, he's probably, I don't know if he's actually German, but his name comes from German, so it's actually Euler. Just like in Germany, you pronounce it as Europe, as opposed to Europe. So, okay, so Euler's method is a method for not solving differential equations because it's too hard. Okay, so you have a differential equation and you decide that it is too hard to solve it, and so you don't. But you don't solve it by using Euler's method. So we could, or our final thing is that we could give up. So Euler's method is a method for giving up, okay? We're going to find the answer to our y at one particular x. Okay, so suppose we're going to have the one we just had. Well, let's do this one. Okay, so here's an example. So here's an example. We have the derivative of y is 2y plus x. We don't have tools to solve that in Maths 1M. There are tools for solve it in Maths 1B, but we don't have them. So that's a good choice. And you know I have an initial condition. Pardon me. Let's just suppose that y of 0 is 4. And what you want to do is you don't really want the formula for y because that's impossible at this time, or you don't care. You just want to know what y turns out to be when x is a particular answer. Okay, so what you want is like y of, say, 2. Okay? Or 10, or whatever it is that you want. So Euler's method is a way of figuring out what y is at a particular x without having to actually find the formula for y. And it works something like this. We're going to use this thing they call linear approximation. Let's see if I can remember how this works. Or look it up in the yellow book. There it is. So we're going to use this. Y of a plus h is approximately equal to y of a plus y dashed of a times h. Yay. So what we're actually doing there is we're getting, this is the point before where we're up to. H is a distance that we want to go. And what we're doing is we're approximating the curve at that point by its tangent. And we're following the tangent to where it ends up and assuming that that's going to be not too far from where the curve actually is. Okay. So what we're going to do is we're going to use, that's what we're going to use, but we're going to use Euler's method with I don't want to go on too long, do I?
In the exams, they generally is a half, 2 steps. That's it.
Let's do 2 steps. Okay, and I hope that it's not too small, but that's to show you what's going on. So sometimes they'll tell you what h is, and sometimes they'll tell you how many steps there are. And either way, it doesn't really matter, because if it's 2 steps, then you're going to divide the interval between the number you know, which is 0, and the number you want, which is 2, into 2 pieces. So h is going to be the distance between 2 and 0 divided by the number of steps. So this is the one I want, I know, and this is the one I want, and this is the number of steps. So h is 1. Cool. So I'm going to work my way through and use that formula multiple times and use the answers that I get at each stage to figure out what happens in the next stage. So to begin with, I have that y of 0 is 4. Okay? And I also have that y dashed of 0 is 2 times y plus x, right? But y is 4 and x is 0. So I get 8. All right, so now we want to go up one step of h. So we're going to go up to 0 plus h, okay, which is 1. Okay, so this is plus 1h. Okay. So y of 1, according to this formula, is approximately equal to y of 0 plus y dashed of 0 times the h. Okay, so we go to the previous step and we use y0 and y dashed of 0 and the h that we've gone, and we figure out what that is. So y of 0 is 4, y dashed of 0 is 8, and so I get 12. Okay, but before I move on, I'm going to need to know what y dashed of 1 is, because I'm going to need it to figure out what y of 2 is. So, according to this, this is 2y plus x, right? And according to this, y, when x is 1, is 12. And x is 1. So I get 25. So to get y dashed of 1, I use the value that I just found for y. So this went in there. And note that this went in there as well. Okay, and then I'm going to plus another h. And so y of 2 is approximately equal to y of 1 plus y dashed of 1 times 1. And y of 1 was 12, and y dashed of 1 was 25. And so that's coming out to 37. And that's my answer. Okay? Cool. There you go. And I can stop there. If I was going further, I would figure out what y dashed of 2 is, and then I would go to the next step and I would use those two answers to figure out the next one. Now, your lecturer would probably have used a table, which is my first instinct, but you do whatever works for you. But it is really important to organise what you've got on the page so you don't lose track, especially if any of these have minus signs, because you'll lose minuses if you're really uncareful. So I find it extremely helpful to separately write what the derivative is at that spot as its own formula, rather than subbing it in as you go, because otherwise you'll lose track. That's Euler's method. Yay, okay, cool. Right, I think that'll do for differential equations, unless anyone has any more questions now before we move on to any other questions about any of the rest of the course. No? Cool bananas. So, I've got about 50 minutes, so anyone got a question? Yes, Jolie.
You do solve for x, ln x minus ln bracket x minus 1 equals 1.
Okay.
It's question 4a of 2011.
So this is 2011 4a, presumably in the calculus. All right. Let's just
Change it.
and really hope that I get solutions at all. Okay, so this is a slightly different question. It's not quite that question, because you need a chance to do it yourself if you can. So, right, and we want to solve this, which means that we need to find all the x's that make this equation true, which means we need to get x on its own if we can, which means we need to get rid of those annoying ln's. And if we did e to the power of x, that would get rid of the ln's, but there is this annoying thing that there is this plus here. We could shift ln x to the other side, but then there's this 1 here that's a little bit distressing as well. So we've got a few options for what we could do. We could do to the e to the power of both sides right now, and that would work eventually. Or we could bring these two together into a single ln. Okay? So, in fact, yeah. Just give me a second. I want to change what this number is. I want to change the question so it has an answer. Okay, cool. In fact, Yeah, that'll do. So ln x plus ln of x plus 2 is 1. Okay. Oh, crap, that's not going to work either. Just give me a minute. 3. Yes, that will work. Okay. So, if I can combine these two together into a single ln, then I can do e to the power of x to get rid of them. So, the rules for ln say that plus outside ln is times inside. Hey, it's so not going to work. That's okay. All that pain for no gain whatsoever. It's going to be awful, just to warn you. So what's happening now is I can now do e to the power of both sides. And if I do e to the power of this, it'll get rid of the ln. And e to the power of 3 is, well, whatever e to the power of 3 is. Slightly less than 27. Possibly even less than 26. Okay, and now we have this awful quadratic equation to solve.
If you made that 3 and 0, that would work.
No, it still wouldn't work. It might not have any solutions at all. All right, so let's just power on. So look, that is an awful number, and I really would have preferred it to be just a 3. Maybe if I put ln 3 there, that would have been nice, but it's not. But all the same, even if something like this happens to you in an exam, you're still going to have to continue. So the only way I know how to solve that is with the quadratic formula, or possibly completing the square. So x is minus b plus or minus the square root of b squared minus 4ac over 2a, which is that. Pretty, hey? If you really, really wanted to, and to make your marker happy but that it matches their solution, you could notice that there's a 4 in both of these, so I could bring the 4 out. But it's probably not worth the effort in an exam. Whoop. And then the square root of the 4 can be done separately. And now everything can be divided by 2.
Would that be negative e to the 3? Would it be
No,
negative?
it's minus 4 AC.
Yeah, because it's minus 4 times a times c, and c already had a minus. Okay, and they are the solutions, except that only one of them is actually a solution.
Why is only one a solution?
Here's the thing. Watch closely what happened as I did this. So as I did this back here, when I turned this into that, more numbers satisfy this equation than satisfy this. Okay? In order to be allowed to do this, both x and x plus 2 have to be positive.
Why?
Because you're not allowed to do ln on a negative number. Because remember, ln is the opposite of e to the power of, right? It's the opposite, it's the inverse function. So e to the power of stuff always produces positive answers. You can't get a negative when you do e to the power of something. And so notice that, I need to draw a picture of that. So e to the power of x as a function, you can put any real number in, but it only spits out positive numbers, right? ln is the opposite, being the opposite function. You can only put positive numbers in, but you can get any real number out. Okay, because it's the opposite function. It's designed to undo e to the power of x. Unless you're in Maths 1a, in which case ln x comes first, and e to the x is designed to undo that. But either way, because e to the x is the opposite of, because ln x is the opposite of e to the x, and e to the x can only produce positive answers, ln x can only work on positive questions. So, that is a fundamental truth about ln, is that you can only have positive things to go in it. So both of my x's have to be positive, because right in the original equation I had ln x all on its own. So since original equation had ln x, right, x must be positive. So, in fact, x is equal to minus 1 plus 1 plus root e cubed. Because if I chose the negative one, I'd have minus minus, which would still be minus, so I wouldn't be allowed to put it in there. The reason that happens is that if both x and x plus 2 are negative, if both of them are negative, then when I put it into this formula, those negatives will cancel out to become a positive because I'll multiply them together. And so I would actually be allowed to do this, even though I can't do this. So by combining these into a single ln, you've introduced extra solutions. So you should always at the end go put the answers you've got back into the original formula to see if they actually make sense. Okay, so you only get one answer. And this is positive because 1 plus e cubed is a little bit more than 1. And so this is a little bit more than 1, so the minus 1 doesn't quite bring it down to being negative. But if it did, then there would be no solutions at all. Okay? And if way back there we had had a 1 minus e cubed, there would be no solutions at all because that would have to give me a complex number answer. And you don't even know what ln means for complex numbers, so there would be no solutions at all. All right? Cool. With a division, with a minus, of course, here, that would become a division. It would be x divided by x plus 2. And so you would actually only get one solution anyway, which is why they did it in that exam, I imagine. Okay. Any other questions? Other than Jolene? Yep.
Could you do something on like the complex polynomials?
That's question 2.
Cool. I've just been asked, can I do something on complex polynomials? So something along the lines of find the roots of this polynomial even though they're complex, that sort of thing?
Examples.
Yep, go for it.
Okay, hang on, let me
Maybe from the assignment.
Yep, has someone got assignment 12 on them?
Yep.
Because if I do it from the exam, that robs you the chance of practicing with an exam, which is important.
There's that one, but there's a harder one.
Okay. So in assignment 12, there's a couple. There's one here. There's several. Okay. Let me do question 8 on assignment 12. So assignment 12, algebra 8, which is P of z is z to the 4 minus 2 plus I times z squared plus 2i z plus 2 minus 4i. Okay, so given that 2 plus I is a 0, find all the zeros. Okay. So David's method of doing worked examples is to try and show you the thoughts that are going on in my head while I attempt to solve them, in the hope that you will know what to think as well. Because if I just wrote it down, that would be no better than having the written solution, which you have. So let's hope that I'm doing that. And if you want to know how I did anything at any point, if I don't say it, please stop me and ask, okay? So I've been told that, just to note that my 2's look rather like z's, I will put a cross through my z's so you can tell. Unless they're actually part of a word, in which case the context tells you that it's a z. Okay, so I know that 2 plus I is a 0, which means that when I sub 2 plus I into that formula, it will come out as 0. But it also means that I should be able to factorize it with a z minus 2 plus I. So this fact here that we've been told says that z minus 2 plus I is a factor of pz. That's the factor theorem. or remainder theorem, whichever of them you like, but technically this is the factor theorem. Because that is a 0, it must be possible to factorise this to get a z minus 2 plus I. That goes no matter what the zeros are, whether they're real or complex. So that's message number 1 from this, is that the things that you knew about real numbers also work with complex numbers and polynomials. Okay, that's cool. And if I wanted to find all the zeros, if I could achieve that by hopefully factorising the entire polynomial, which is the hope. So I could divide this by that and tell me what's left, and that would factorise it. I might just need to turn my page sideways.
With long division?
Yes.
Oh my god.
Well, I mean, it's the first thing I've thought of. Okay. I can't think of any other way of dealing with that. Because, let's just go back. If it was a real polynomial, if these were real coefficients, then I would know that 2 minus I would be a 0 as well. Because if all of them are real to begin with, the only way to get a complex number is to get its conjugate in there as well. So if these were all real numbers as the coefficients, 2 minus I would be a coefficient, would be in there too, and I would be able to get z minus 2 plus I and z minus 2 minus I, and that would give me a quadratic, but it's not, it's complex, so I have no guarantee that the conjugate is a solution as well. So the only thing I can do is divide, and so divide, so divide p of z by z minus 2 plus I. Now, I have a feeling that's going to take me some space, so I'm going to turn the next page sideways. So we have z minus 2 plus I, and I want that to go into z to the 4 minus 2 plus I z squared plus 2iz plus 2 minus 4i. And I've given myself plenty of space in case, you see I've given myself a bit of space here in case the coefficient that comes in has a real number part as well, because currently it's only got an imaginary part. Okay, so z goes into z to the 4, z cubed times. And z cubed times this is z to the 4 minus 2 plus, oh crap. It wasn't a z to the 4 to begin with, it was a z to the 5, z to the 3, which is so much easier. Gosh, I feel happy. The original question had a z cubed here. Now let me tell you what went through my head to decide that I had written the question down wrong, because you need to know that too. I noticed that I was going to get as 2 plus I times something here, and it was going to be a z cubed, not a z squared, but if it was a z squared it would neatly cancel out, and that would be nice. And so I was really hoping that the person who wrote this question would be nicer to me, and so I went back and checked that the question was actually, to see if the question was actually easier than I thought.
So you'd still do long division?
Yep. So z cubed divided by z is z squared times z is z cubed, z squared times this is that. And I have to subtract that off. And so I get this minus that is 0, this minus that is 0, this minus nothing is 2iz, this minus nothing is 2 minus 4i, and that's what I have next. Okay, so I got 2 zeros here technically. So now I'm up to here, and 2iz divided by z is 2i. Okay, and let's see, 2i times z would be 2iz, as it should be, and 2i times this, oh dear. Okay, so 2i times minus 2 would be minus 4i, and 2i times minus I would be minus 2 times I squared, and I squared is minus 1, which would be 2. In fact, let's just make it wider. So we have 2i times minus 2 would be minus 4i, which I wrote here. And the 2i times minus I would be minus 2i squared. But I squared is minus 1, so it's just plus 2, which I wrote here. And you'll notice that these neatly and conveniently cancel each other out. Okay, and so therefore P of z, this is P of z, is z minus 2 plus I times z squared plus 2i. Yay. So in order to find all of the zeros, now I need to factorize this. Or at least make it equal to 0 and solve the equation, right? Okay. So now, so P of z equals 0 will indicate that either z is 2 plus I, which is this bit here, or it will be z squared plus 2i equals 0. So just to be absolutely clear, we'll either get that or that from those two factors. So z is 2 plus I, or z squared is minus 2i. And I need to square root minus 2i, which means I need to square root I. Damn. Well, the only way to square root complex numbers is to use polar form, usually. Well, I didn't say it was going to be easy. So that would actually be like, so where's minus I is here, there, yeah? So that's going to be 2 cis minus pi on 2. Yay. Almost there. But also any multiple of 2 pi on top of that would give me the same answer. So knowing in advance that it's a squared here, I'm going to get 2 answers. So I can just use the plus or minus if I want. Otherwise, I just go another amount of 2 pi from there and I can get the same thing. So I can actually get 2 cis 3 pi on 2 is another perfectly good answer, which is going this way. So I can go this way and get there, or I can go this way and get to the same spot. Or alternatively, I could put a plus 2 pi k there and that would be fine as well. But, and technically there's infinitely many choices because I could go another pi on 2 and get, oh dear, 7 pi on 2 and another pi on 2 and get whatever. Okay, so I only need 2 of them because it's squared. And I know there's only going to be 2 answers because squared quadratic equations can have at most 2 answers. And so the Moira's theorem says that when I do a power, such as a power of a half, I just do that power on the number and multiply that power by the angle. So the half, I'm doing a power of a half to get rid of the 2. 2 to the power of a half is root 2. Cis minus pi on 2 to the power of a half means that the half multiplies by the angle. And the same thing here. So they're my 2 answers. And I guess for completeness sake, I should probably put them back into rectangular form. But that's actually a perfectly good answer at the moment. I've got all 3 solutions. 1, 2, 3. Yep.
So you could have gone now and added 2 pi to it, and
I could have, yeah, or I could have subtracted 2 pi. So I could have actually gone down to minus 5 pi on 2, and that would have worked as well. But I wanted my numbers, my angles to be as small as possible. So that's why I did the 3 pi on 2, so that, because if I went 5 pi on 2, that's a big size. Yep.
Is that what they mean by the principal argument?
The principal argument is, yeah, okay. So the principal argument is an angle in there. It's between plus pi and minus pi. That's right. So it's the angle of smallest size, regardless of the plus or minus, that gets you to that same point. So with the one final addendum that, of course, minus 1 has principal argument pi as opposed to minus pi, because pi is simpler than minus pi to write down. So it's the angle of smallest size. So if it's down here, you want to go minus something as opposed to plus something the other way around. So back in this one, that there, the minus pi and 2 is the principal argument, but this is another different argument you could have chosen. Cool, is that all right?
Yeah.
So obviously, that question is awful and probably would not appear in that form in an exam. Okay, it would be much more obvious. Maybe the other part would be z squared equals 1, like z squared plus 1, and which would be much easier to solve. Okay, or it would be something more like this has only real coefficients, in which case the 2 plus I would be matched with a 2 minus I as well. And you could just divide by that quadratic and give you a linear one left behind. But all the thinking that went into this was the same as for all polynomials. Like if I have one solution and I don't already know just how to find the other one, I can always use polynomial division to find the rest of the polynomial. Okay, even if it's complex numbers. The worst thing that would happen would be if there is a complex number here as well, in which case I would have to divide by complex numbers in order to do the long division, and there would be all sorts of other working as well. But that's just too much work for an exam. Unless, of course, in part A, they've asked you to divide those, and you should notice that you've already done that division elsewhere. Okay? But look, I would not write that if I were writing an exam. That would take a certain level of sadism to write that for students in an exam. Right, any other questions? Yes?
Can you do z to the 5 equals minus I, finding exact values in polar form using the principal argument?
Okay. Z to the 5 is minus I. When was this?
2009.
What question?
Question 7, part C.
Okay, just so people know where it is. So that's the 2009 exam 7C. And we want to find all solutions
In polar form.
in polar form. That's good of them. With exact values
Using principal argument.
and principal argument. Okay, cool. The exact values is going to be easier in polar form anyway. So this, don't do decimals if there's a root, and don't do pi. Don't figure out what pi is. Just leave it as a pi. That's what that means. Principal argument means I'm going to use the smallest sized angle that I can for all of those points. And polar form, it's going to be something cis something. So that's good. And all the solutions there ought to be 5. Because it's z to the 5. Okay? That's how polynomials work. A polynomial with 5 as the biggest power ought to have 5 solutions. It may be that some of them are equal to each other, but in general there will be 5. And if we're using complex numbers, the only way to have less than 5 is for a couple of them to be equal to each other. Okay? You can't get no solutions because all polynomials have solutions with complex numbers. Okay. So, it's going to be, I have to do a 5th root, and polar form is one of its reasons for being is for doing powers of complex numbers. So I need to rewrite I in polar form now.
Minus I.
Minus I, yep. So let's see. So there's minus I there. So let's see, minus I is, let's see, it's cis of minus pi on 2, yeah?
Do you need to plus 2k lots of pi on that?
Yes, I'm getting to that.
Sorry.
One step at a time. That's what cis is with one angle, right? But the thing is that the reason why you get multiple solutions when you do roots is that there are multiple ways of representing this number. So, but that's the first thing I would write down. And then I would say, well, this is actually equal to cis for any integer k. Something like that. So I can get that minus pi on 2, and I can go any multiple of pi, 2 pi, and I will get to the same place on the unit circle. So the idea is that I can get from here to here, and I can also go around another 2 pi and get to the same place, and another 2 pi, or possibly this way, and it would come to the same answer. Now I could actually shortcut this, knowing that there's going to be 5 answers, and actually just choose 5 different options for what this could be. But at the moment, this is the safest way to run with it. For the other one, because there are only 2 answers, I just wrote 2 options for what k is. Okay, but since there's 5, I'm going to skip that for now. So what we've got now is that z to the 5 is cis minus pi on 2 plus 2 pi k. The length of I is 1, right, which is why there's no number here. Okay? Because remember, normally you'd have the length of the number out the front here. So now I need to do all of this to the power of a fifth. To be completely clear with my working, I've done all of that to the power of a fifth, but powers of cis means that the power can be brought inside the cis as multiplication instead. So a fifth of minus pi on 2 is minus pi on 10. And a fifth of this is 2 pi k, 2 fifths of pi k, right? Cool, that's what z is. It could be any of those things. All right, but notice that if k is a multiple of 5, if k is a multiple of 5, if k is, say, 5, I'm going to get 2 pi, and adding 2 pi to the angle doesn't change what the complex number actually is, okay, because going around another 2 pi gets you to the same place. So I can choose k to be any number as long I only need to choose 5 different options for k. So k is a whole number. I'm just going to draw where they are so I can pick their principal arguments. So we've got minus pi on 10, which is sort of here-ish. That was the first one. Minus pi on 10. So it's negative, which means it's down here, and I divided that pi into 10 pieces. So that's the cis of minus pi on 10. I can go 2 fifths of pi. So I can go multiples of 2 fifths of pi from there. So there'll be 5 of them, and they'll be spread evenly around here. Probably like that. That's my guess, can't be sure. But they will be spread evenly around this circle, and the distance from here to here in terms of angle from here to here is 2 fifths of pi. So it looks like we're going to get 2 in the negative, and 3 in the negative, and 2 in the positive. So, I don't know. So we've got minus pi on 10, minus pi on 10, plus 2 fifths of pi, which looks like the safest way is actually to go plus 4 tenths of pi. Oh, that's going to make it easier. Let me go back here. Just write this one in terms of tenths so they're easier to add together. That's going to make my life easier. See how this is in tenths of pi? I can write those 2 fifths in terms of tenths as well, and then they're going to be much easier to add. Cool. Let's just change that. So if k is 1, I've got 4 tenths of pi, so that's 3/10 of pi. And then we've got plus 2 times that, which would be 8/10 of pi. Cool. If we go another 4/10, we're going to go beyond pi, right? Because we're going to get to 11/10 of pi, which is beyond pi. So we should probably go the other way now. So that's minus 5/10 of pi, which is actually minus pi on 2. And minus 8/10 of pi is actually minus 9/10 of pi. Okay, so there's our answers, and they all just have sis's on them. So I probably shouldn't have wasted my time writing them all out separately, but there you go. So z is, in fact, cis of minus pi on 10, cis of 3 pi on 10, cis of 7 pi on 10, cis of minus pi on 2, and cis of minus 9 pi on 10. And they are the 5 answers. How do you feel about that?
It's good, I just made a silly mistake up here, so I can see what I did wrong.
Yeah. So, how someone said, I made a silly mistake. How are we going to avoid silly mistakes? You don't know? I did some things for myself that made it easier. One was rewriting it as tenths here to begin with. That made my life easier. Also, always drawing the picture, but hopefully you've got that before you figure out what it is in terms of cis. And putting this in as a plus 2 pi k to begin with. And actually I also wrote in everything to the power of fifth first so that I didn't lose it along the way. And it reminded me that I had to multiply both of those by a fifth. And also, one way of noticing if you've got problems is that if you do this trick and you end up fitting in more in around the circle than 5, then you've done something wrong. So, yeah. All right. Any other questions about anything at all?
I have more questions.
I've got one.
Yep.
Limits. If you've got the limit as x tends to infinity of 3x squared take x take 1 divided by 2 take 3x squared take x cubed. How do you deal with the whole infinity situation?
All right, so I've been asked what this limit is and how to deal with that. And we've got how to deal with the whole infinity situation. So we've got two things. We've got this infinity here. So, first let's ask what would happen if this wasn't infinity, if this was a proper number. If this was a proper number and when you subbed it into the bottom you got 0, in general it wouldn't exist. So the rules generally go, if the top and the bottom are if the top is 0 and the bottom isn't, then the answer is 0. And if the top isn't 0 but the bottom is, then the answer doesn't exist and is one of the plus or minus infinity. And if they're both 0, then it must be possible to factorize the top and the bottom to cancel something out. And then you try again. Okay? But with infinities, that's a whole different story because infinity isn't even a number. So we can't sub infinity in because it doesn't work. But in general, let's think about what this means. This here is 3x squared. If x is, say, let's just think about what would happen if it was like a billion. We have 3 billion minus a billion minus 1. And we have here 3 billion. That's 3 billion. So the idea is that, look, a billion is shockingly small relative to a billion. So the only things that matter are the biggest powers. Okay? And x squared, a billion squared, is shockingly small relative to a billion cubed. And so the bottom is hugely bigger than the top. So this is approximately 0. That's what you would do in your head. What you would write on paper is this. Okay, but you can see that the bottom is hugely bigger than the top, and so we get 0 because we get small number divided by big number. Okay, if the top is bigger than the bottom, it won't exist. Okay, because it'll just go to infinity. And if they're roughly the same size, it'll come out to a number, and it'll come out to, if this was this, I'd have 3x squared divided by 3x squared, which is 1. Okay, so, but in order to do it completely formally, what we can do is this: we can divide the top and the bottom by the biggest power of x. And that's the biggest power of x that appears in the entire fraction. Okay? By the biggest power of x that appears in the whole fraction. Okay? So don't just use the biggest power of x that's on the top. Don't just use the biggest power of x that's on the bottom. You've got to find the biggest power of x in the whole fraction. So I've got that my limit as x goes to infinity of 3x squared minus x minus 1 over 2 minus 3x squared minus x cubed is the limit as x goes to infinity of, and we're going to divide everything by x cubed because that's the biggest power that's in the whole fraction. So 3x squared divided by x cubed is 3 on x. And x divided by x cubed is 1 on x squared, and 1 divided by x cubed is 1 on x cubed. Okay? And this would be 2 on x cubed, this would be 3 on x, and this would be 1. So now, the limit of the top, as x goes to infinity, is we've got 3 divided by infinity, which is 0, 1 divided by infinity, which is 0, 1 divided by infinity, which is 0, so the top is 0, and the bottom is minus 1. And so we get 0 as the answer. Sorry? Neat. And if the top had come out to something not 0 and the bottom had come out to 0, you would be able to say, you would be able to put in inverted commas, 1 over 0, you say, does not exist. Okay? That's the neat version. Okay, so you're always allowed to divide the top and bottom by something that's not 0, and infinity is not 0, so we can do that.
Another limit that stopped me. Limit of x tends to 0.
Just give me a second. So, just a second. Yep.
Sine x over sine 6x.
Right. Now, if you had been in Maths 1B, you would have used L'Hopital's rule, which some people have looked up on the internet, but you're not, and it's not necessary. So, right. We need, so let's just check. If we sub it in, we get 0 divided by 0. So sine 0 is 0, and sine 6 times 0 is still 0. So 0 over 0 tells us nothing, so we have to do something else special. So tell me a limit that does involve sine that you do know the answer to.
Sine x on x is 1.
Okay, so what we do know, that the limit as x goes to 0 of sine x on x is 1. Okay, that's the fundamental trigonometric limit, and you're supposed to just know that. All right? So, I need to rewrite this to look more like that. So, I'm going to strip off the limit for a minute because I don't want to keep writing it over and over. I need to rewrite this to look more like that. And if I want it to look more like sine x over x, I need to put some x's in. And if I want to do that, well, I have to start multiplying the top and the bottom of the fraction by stuff, or splitting it up. So this would be sine x over 1 times 1 over sine 6x. Cool. And I can actually put an x in both of these positions here. All right? I'm allowed to do that because x is not actually equal to 0, because x just approaches 0. So x is not equal to 0, so I'm allowed to divide by it. All right? And this part, the limit will be 1. This is not quite right. We need, that sine x on x will work even if it's not x. If they're both the same thing, as long as they both go to 0, it should work. So sine x squared on x squared would also be 1. Sine of sine x on sine x will also be 1. Anything that you can put there, as long as they're both the same and they both come to 0, will work. So we really would prefer this to be a 6x. Because then it's sine 6x on 6x. So what we really want to do is we want to do this. And so now, I'm going to put limits in. So the limit of this bit is 1, and the limit of this bit is 1, and the limit of a 6 is a 6th. Magic, huh? Traditionally, this is in one of the assignments, and don't usually get a chance to talk about it at the time, because I don't usually put it in the lectures, because they trust your tutor to do it in the tutorial, forgetting that there's only 1 hour and a whole lot of stuff to do. That's really it. Yep.
X on sine x is also 1.
Yes. Because it's 1 over, right, so technically it's this, right? Just to be really, really niggity about it. Six x on sine 6x is 1 over sine 6x on 6x. Okay. And so the limit of that is 1.
Yeah.
That's being really technical about it. Yeah. All right? Okay, never be fooled by that again. So it works with tans and everything else. If you split all the sines into having a separate thing on the tops and bottoms, and everything else that won't come out to 0 anyway, just leave it, and you can sub it into that part. Cool. Any more? We've got 8 minutes.
Trigonometry?
I'm going to, okay.
Can you get the drawing the tangent angle sum formula using sine cosine?
That's a good question, actually, because it shows you some things about how to think about deriving formulas. So I've just been asked, can you talk about deriving a trig formula going from one side to the other? Which is probably what people are going to ask about anyway. So there's the traditional one that goes... So it's nice when people all have the same questions. You don't feel like such an idiot if other people have the same question as you. There's this one that says, like, show that tan of alpha plus beta is whatever it is. Does anyone know what it is off the top of their head? Can you look it up? I think it's like tan alpha minus tan beta on 1 plus tan alpha tan beta, something like that. It's whatever it is. Okay, I'll figure out what it is in a minute. But, yep?
Tan alpha plus tan beta on 1 take tan alpha tan beta.
Okay, so the nice thing about this is they'll often give you both halves, and you'll know what you're headed for. I'm going to sharpen my pencil. They could give you any trig formula, and the same thinking is going to be applied to both. You're not expected to remember the tan double angle formula. It's not worth the pain, because you can remember the tan angle formulas, because you can remember the sine and cos angle formulas anyway. And that's what it's all based on. So if you're going to show that that is true, we need to use facts about tan and other stuff in order to make it work. So there's two approaches to this. We can try and get from here to there, or we can try and get from here to there. And there is a third approach where we start with both of them and do working on both until they come out to the same answer. Whichever of those is the first thing you think of is the one to do, because you haven't got time to make a decision. I am going to start here because I feel like it. Often it's easier to start with the complicated one and make it look simpler because it's easier. No, other way around. Often it's easier to start with the simple one and make it look more complicated. Okay. Because it's harder to simplify things if you've got to bring brackets together that you can't see in advance. It's easier to expand things out than it is to factorize. Okay, so I'm going to start here. And I know that I can't just sub in angles for alpha and beta because it's supposed to work for all possible alpha and beta, so I have to use algebra. I'm not allowed to just sub stuff in. If I was told to verify that this is true for alpha equals pi on 3 and alpha and beta equals pi on 4, then I could just do it. I could just sub them in because it says verify, which means basically sub in. But it says show. All right. Well, tan is sine over cos, so that looks like a reasonable place to begin. Good-o. There is no real method, right? We need to think of things that are going to help us think of what to do even though we've never seen the problem before. And that's the first thing that occurred to me, that tan was sine over cos. And the nice thing about it is that it's already written as a fraction, which is what I'm headed for. I know I'm looking to write it as a fraction, so writing it as sine over cos seems like a good move. And now there are formulas for splitting up sine and cos for alpha and beta, because I know that I have to get the alphas and betas out of the tan. So that would be sine alpha cos beta plus cos alpha sine beta. And this would be cos alpha cos beta minus sine alpha sine beta. In case you want some advice on how to remember that, I can tell you what I did when I was in year 12, and it's to remember that cos is antisocial and sine is sociable. You see, cos keeps the coses with the coses and the sines with the sines, whereas the sine puts the sines and coses together. And cos is even more antisocial because it puts the minus sign with the sines, you see, because they don't deserve a plus. Yeah, I don't know. Not many people associate personalities to functions, but I think I'm vaguely synesthetic. Okay, so I also remember them because they match with the double angle formulas, which I find easier to remember. So I know that sine of 2 alpha is 2 sine alpha cos alpha, so I know that sine has to put the sines and the coses together. Otherwise it wouldn't come out right if beta is alpha. Okay. Right. So now I want to make this. Oh, I've made it bad. This has to come out to be equal to that. I'm doing well. I've got a minus sign in the correct spot. I've got something minus something, so that's a good move. It's good at every stage to compare what you've got with what you're headed for. So I would really prefer this to be a 1 here. That's what I would like. I'd really prefer this to be a 1 in this spot. Or possibly this to be tan alpha, or possibly this to be tan beta, or any one of those would probably be helping me make my decision. Well, I could make this a 1 by dividing the bottom by cos alpha, cos beta. It's a plan. And if I'm going to divide the bottom by that, I have to divide the top by that as well, right? So what I've done is I've divided everything on the top and everything on the bottom by cos alpha, cos beta, and I did that because I wanted a 1 in this position to match with the 1 in this position. I'm trying to make it look like the thing I'm headed for. Now, if I didn't have a formula to head for, I would be trying to produce tans in my picture. And so I could have produced those tans by dividing by coses, or, all right, because sine divided by cos is tan. So let's just have a look at what we've got. Cos beta divided by cos beta, and they'll cancel, they will cancel. Look, sine alpha on cos alpha is tan alpha. Sine beta on cos beta is tan beta. Sine alpha on cos alpha is tan alpha. Sine beta on cos beta is tan beta. Magic. That's what I was looking for. Now, when I first did that, I did not know that was going to work. I mean, I did now, because I've done this problem every year for the last, 7 years. But when I first did this problem, I didn't know it was going to work, and I had to just try something. So I want to make it as close as I can to the answer I'm headed for. So I wanted it to be a fraction, so I wrote it as sine over cos. The only thing I knew to do with the sines and coses is to split them up with their own formulas. And then I had to stare at what I've got and said, how can I make it look more like what I want? I can get a 1 here by dividing by whatever's there. Now, that dividing by whatever's there might not work in the problem that you're looking for, but it's a useful trick to know. Okay, to divide the top and bottom by something to produce a 1 in a particular spot. I could just as easily have stared at this sign here and said, well, I wanted a tan alpha in that spot, so I could divide by cos alpha and see what happens. And that would get me the tan alpha in the correct spot. And then I don't want the cos beta to be there, so I divide by the cos beta and that disappears as well, and now everything works out. So there are several rows to that same place. I chose the quickest one, but that's because I knew, that's because I wanted to get the 1 first. But I could focus on any of those and work. And all things to do with proving one formula is equal to another are the same. Okay? You're generally always allowed to assume those angle splitting formulas for sine and cos, and the double angle formulas, and of course the definition of tan and cosec and sec. So there's all sorts of ones about, sec squared something is equal to some weird 2 fractions. So whichever of them is easier. If I saw thing that was 2 fractions separately and I wanted it to a single answer, I would start with the complicated one and put them over a common denominator, because that brings 2 fractions into a single object. Right? So look at what you've got and make a decision about how to get from one side to the other in any way at all. But what I definitely cannot do is start with this and work on this formula, because that assumes that this is true from the beginning. I have to start with one and get to the other. Or start with both separately and get them both to the same place. Cool. Now, Nicholas is probably dying in the Maths Learning Centre, so, because Maths 1A is a much bigger course than Maths 1M, and they're probably all in there. So I'm going to stop now. If you do have any more questions, please come to the Maths Learning Centre or talk to your lecturer, or talk to your friends, and then come to Maths Learning to make sure your friends are right. Yeah, please. I would love you all to pass your exam. Thank you.